Okay? How much is the residual sum of square of this model? What is the residual sum of square? So the residual sum of square is the amount of error I'm doing over all the data I have. So it's a summation over all the data of the true y for a single sample minus the prediction I gave for that sample. So here the prediction is given by the linear model. So how's the formula for the prediction? W0 plus W1 x y1 plus 2x y2 plus W3 x y3, where these three values are the three inputs we selected from a specific sample. Okay? Well, I cannot spot here the residual sum of square directly, but I spot something which is related to the residual sum of square. There is the root mean square error. What is the root mean square error? It's nothing else but the version of the RSS which is corresponding to the error of a single sample. So we just use the RSS, we do the square root, and then we divide by n. This is the average error I'm doing on a single data. So if I'm predicting a new point, probably I will have an error which is likely to be something like that. Okay? So, okay, we just have to not sure about that. Yeah. Like that? Yeah, I think it's better. Okay, so just we can compute the RSS as n times RMSE squared. Okay?
Okay.
Yeah, like that. Okay? Okay, so the fifth question, how much error is the model making on average on a new data point, is nothing else but the root mean square error. While for the variance explained by the model, what can we look at? Yeah, so the R-square coefficient is a coefficient which tells us how much variance is explained by the model with respect to the total variance of the data. In this case, R-squared is 0.51, So it means that roughly half of the variance of the data is explained by the model. Okay? The more the data are, let's say, line-shaped, the more the model probably will be able to explain the variance, so the more the R squared will be high. Okay?
R squared or R squared adjusted?
Okay, what's the difference between the two? R squared is just this value, while the R squared adjusted is trying to also adjust this value with respect to the number of parameters I'm using. If I'm using a model with a lot of parameters, so a really complicated model, probably I will be able to have a really high R squared, since I'm, for instance, interpolating my data, but this is not a good choice. I'm not producing a meaningful predictor. The R squared adjusted adjusts with respect to the number of parameters, so if there are a lot of parameters, it will lower the value of the R squared. So it's somehow balancing between the complexity of the model and the accuracy of the model. Okay? In this case, we have 99 observations in just 4 parameters. So the two will be more or less the same. In much more complex model, the R squared and R squared adjusted might be really different one from each other. Okay?
So since the question is asking us the effect of the model on a new data point, we should also consider the overfitting of the model. So we should
okay. Just by looking at the model, if we look at the model and we think that the model is meaningful, then probably the RMST will be that estimation. I agree with you that if I'm overfitting, it is likely that I'm not guessing so good. Okay? This is an average value, by the way. So you don't have to expect that every time you will have exactly that error. You will have that, on average, you will have that error. Okay? But I agree with you. I mean, if you have a really overfitted model, probably the average error might be way large.
But that one is the average error on the training point. Right?
Okay, but that's also an estimation. If you did everything right, and also the training set and the test set are coming exactly from the same function, the same distribution, then you will have that the error on the training point, on the training set, will be more or less the same on the test set.
Except for the fact that the model can be overfitted.
Yes, we will see how to cope with this kind of problem in the next lecture. I agree with you. It is not that every time RMSE is predicting your error. There are other techniques in order to predict, let's say, to have an estimate about the error of a new point. This is a rough estimate, okay?
Could you please repeat how we should answer to the fourth question?
So to the first question, I will have that fourth.
The one with the R squared.
R squared, okay. So R squared is the percentage of variance explained by the model. If you have R squared equal to 0.51, it means that 51% of the variance, of the total variance of the data are explained by the model. Clearly, if this value is really high, we are really happy, since, okay, apart from overfitting effect, if this value is really high, it means that we are somehow explaining more or less all the variance we have in the data, all the variation we have through the x. While if this value is really low, probably there is no correlation between data also, and so probably the model is not unique. So I want R square approximate to 1. If I have R square equal to 1, I'm okay. Not equal to 1, it's near to 1, I'm happy. Okay? I want to stop for 5 minutes, since I'm a little bit tired, and then we can go to the theoretical exercise, okay? Toy question, okay? This is the toy question. Given the expression, that expression, you have to tell among these which one are the response, independent variable, feature, and model. Okay? Again, an answer, this one is not enough. We have to motivate. Okay? So, first, what's the response of this model? So it's a model, okay, a regression model somehow, since it's predicting the amount of sale revenue given how much I'm investing in advertising on radio, on newspaper, or on TV program. Okay. So what's the response of this model? S. Why S? Since S is the variable which I'm interested in, is the variable I want to predict. So it's the output of the model. Okay? That's enough. One line. Okay? But just S, that's 0 point. Okay? What about the independent variables? Or the other. Okay? So it's TP, R, and N. These are variables since these are the input of our model. What about feature? Feature is just an alias core variable, okay? So again, these are all the inputs I have. And for what's the model? Well, that's the only stuff. It remains, so that's F, okay? It's the model, or the, yeah, the model. Please. No. Wait, if the problem is to predict S, I cannot consider S as a feature, because otherwise my problem is solved.
In the sense that in the previous problem we took one of the four variables to be the target.
Yeah, sure. But then, after we choose the target, it became a target, it's a feature no more. Okay? Again, when we will have a new data point, we are expecting to have a value for TV, a value for R, a value for N, but no value for S. Okay? That's the difference. In the new point, otherwise, if I had also S1, okay, I don't need to predict anything. I just have to tell S1. Please.
Features could also be a function of the input.
Sure. Guys, that's a toy example, by the way. Don't try to overthink, okay? That's just to understand how it works, okay? That's the game we are going to play from here to the end of the course, okay? Let's go to the real stuff, okay? Now you can try to overthink. Okay. So. So let's start with something which is more methodological and less formal, I would say. So we have some machine learning problems, so we know that these are machine learning problems, and we want to understand which technique we want to apply to solve this problem. Okay? So we have to categorize machine learning problem. What are the categories for a machine learning problem? Okay, let's say, and okay, so the three big areas are supervised, unsupervised, and reinforcement learning. In the supervised area, we have regression and classification. That's it. Okay, I think you only saw this area, but there are way more areas. For instance, there are some problems which are semi-supervised. There are some problems which are called active learning. Or there are other problems which are called of transfer learning. And usually you cannot categorize this kind of problem in the other classes. Okay? Okay, that's it. So, let's start. The first problem is to predict housing prices for a real estate. Okay? So we want to sell some houses and we want to predict their price. Which kind of problem it is? So, regression. Okay, why? Pricing. Again, it doesn't matter if the prices are continuous or not, if they are ordered. Okay?
It depends on the input variable, like, maybe.
No, the price is ordered,
No.
always ordered.
I mean, if you can put the houses on the X axis.
Well, it doesn't matter, the ordering of the input. What matters is the ordering of the output. For instance, you can have a categorical variable as input, if the house is red or not. Okay? That's categorical, still I can perform regression. Okay? For instance, the color, okay, there is we'll see something like that. Okay? So, it's a regression problem since the price are ordered. Now let's try to think about some kind of input we can use apart from the color of the house. The number of rooms or the square meter of the house. Okay. Or the zone where the house is, or if it has a space for the car or not, if it has a garden, something like that. Okay? Which techniques could we use? Regression, linear regression. Okay? 2. Please.
Should we choose anyone in particular to be supervised or reinforcement learning?
You should some argument. Okay, why it is a reinforcement learning problem?
I actually don't know how it works. I mean, I know how it works supervised, but
Okay, so here I'm not excluding that there are other formulations of this problem which could fit the reinforcement learning framework or another framework. But you have to justify what you are trying to write. So if I'm writing reinforcement learning, I should formulate a problem still, which is related to what is written, which fits the reinforcement learning framework. Okay? So I cannot tell you no, it is not. But if you are not giving me the formalization, I can say okay, no. Okay? So I'm open. It's not always yes, it's not always no, it's always it depends, as long as you motivate what you answer. Okay, sometimes it's no or yes, I will tell you why. Okay? Most of the time is it depends. Let's go to the second problem. Identify inside trading among stock market exchange. So here we have some person who's performing inside trading, so he's stealing some information from his company and he's trying to use it for market exchange. Which problem it is? Classification. Why?
We have to identify.
So it's a binary classification. So given a person, given all the features about the person, we want to understand if he's an inside trader or not. Okay? That makes sense. Great. Detect interesting feature from an image.
You put him in one of these classes.
Someone is saying unsupervised learning. Why? Yeah, okay, we do not have anything to predict. We just want to gather information, or we just want to understand if there is a pattern in our image. And that's unsupervised learning. Okay? Clearly, in unsupervised learning, you can perform a lot of stuff. Here, it is more like feature extraction or feature selection. Some other times, you will have the meaning of unsupervised learning, which is more similar to clustering, so the division of your dataset into areas, I would say. Please.
About the second one, I didn't get why we said it's a classification.
Because I want to understand, given a person, given all the features about the person, age, weight, salary, if he is likely to be an inside trader or not. So the decision, the class are, the person is not an inside trader, the person is an inside trader. Okay? I mean, there is no topological, there is no ordering in these 0-1 classes, somehow. You are not convinced. Okay,
Maybe
every time you have just two classes.
maybe I don't know
always
the
order them,
problem.
huh?
Maybe I don't know the problem. Why we should identify a person if it's a trader or not? Or
Because he's stealing money from my company. Come on. I don't want inside trader. Inside trading is against the law. Okay? If I'm using information from my company to buy stocks on the market, that's not allowed. Okay? So the problem is, if I spot somebody who's likely to be an inside trading, probably I will fire him. Okay?
okay.
Do you agree? Do you think it's a good idea?
Okay.
So probably here it was the problem which was not clear. Okay. So let's go to the first one. Determine which verb species is R on a given audio recording. Because we want, okay, let's stay on the third one. On the third one, we have nothing to predict. We don't want to say this image is good, is bad, or this image has a score of 1, 2, 3, 4, 5, 6 to 10. We just want to extract some information. And the task of extracting information from a data set is usually addressed by unsupervised learning technique. I don't know if we will see something like that, but at some point we will talk about PCA, which is a method to compress, for instance, the information about an image. In that case, you do not want to predict anything. You just want to have your entire dataset and try to have a lighter version of your dataset, a more compact version of your dataset. Okay? Can I move? Perfect. So the first one, determine which bird species are on a given audio recording. Classification, because you cannot order birds. Okay. Again, here it might be a problem which is a little bit harder than classification, since, for instance, if in a single audio recording you have 4 words, you will have to output 4 labels for a single input. So it's something a little bit different than the standard. Teach a robot to play air hockey. Okay, that's the most trivial example of reinforcement learning. Why reinforcement learning? The point is that you haven't seen anything from reinforcement learning field, so I would suggest you to wait till the lecture about reinforcement learning to answer properly this question. Okay?
Could we say that is reinforced learning because we don't have any way to say, okay, this action is good or this action is bad, so it is the only way that... I mean, you can just say we use...
You can say, I mean, yeah, win lose is still better than good.
Yeah, but you have no label.
Trust me, let's wait. This time, let's wait, okay? Because we will see, for instance, in some other problem like the in some problem in reinforcement learning, you know exactly the value of each action you are performing. So it is not a matter on if you know your reward or not. It's a matter on how you formulate your problem. Okay. So this problem is you have to decide a policy. So every time you are in a state of your problem, you need to tell which action the robot should play. So it is somehow a task of policy learning, a behavior learning, so it's reinforcement learning. At last, predict taste in shopping streaming. Taste, I mean, predict preferences for shopping or streaming. Please.
Is this a recommended system task?
Yeah, it is. So it's
Supervised.
supervised, I would say. It really depends on how you formulate your problem. If you do not know any couple user preferences, probably it is an online learning problem. If you have let's say large data set about user and preferences, it might become something like a reconstruction problem. You have a matrix which is sparse and you want to fill this matrix. So you can use maybe some unsupervised learning techniques. In the, let's say, most classical way, if you have user and preferences, you want to somehow predict for each user which kind of preferences he or she has, so it's a supervised learning. I would say a classification problem. Okay? Okay. Let's stop now. We will see each other in 1 week. I think I will do some other exercise about linear regression, and then I will move to classification. Again, you will have to read the first part of the PDF before the classes, okay? See you guys.